space and time are.
Okay, so hear me out. I don't think that we truly know what gases are. So we know with fairly extreme precision the structure of solids. We can take techniques such as tunneling, electron microscopy, and shoot electron beams into solids and see all the way down to the molecular lattice structure geometry, where we can see, for example, with like a graphene monolayer sheet, the individual 6 points of the hexagon where the 6 atoms are laid into a lattice ring.
It blew me
It's
away
very
when you showed
precise.
me that. I know, yeah.
Yeah,
Yep.
very, very precise, right? And, similar things we can do with liquids. But when it comes to gases, when an element goes through a phase transition into a gas so that it becomes diffuse and spreads out and floats and does all that stuff, you completely lose any ability to image it, even with things like tunneling electron microscopy. So when this happens, gases are said to be moving at very high velocities, of course. Like in a room, the air molecules are said to be moving at several hundred meters per second. Okay. But there are different techniques, right, that they can use to infer the shape. For example, they can use X-ray diffraction and other things like that, where they shoot electromagnetic waves into it and measure like the angles that it diffracts or reflects off in order to infer the bond angles. For example, with something like methane, CH4, it can exist as a solid, a liquid, or a gas. They say, they can image it with a solid, right? Oh, here's its molecular structure as a solid. Here's the bond angle. Well, when we flip it to a gas, that bond angle remains the same angle, so therefore we assume that its structure is the same structure. And other things like this. But these are all techniques via inference. If our predictions or our models, say that it should be this certain numerical value, it must be this certain shape, right? But that's not a direct measurement, that's an inference, and it's assuming that gases follow all the same rules as the other states of matter do, right? Even if our numerics are correct or we're able to deduce them properly, doesn't necessarily mean that that's the shape. So here's some evidence that would point to that being the case would be when we take gases and we try to image them, we can't, right? There's no way to hold it still to isolate, let me take my tweezers and grab a gas molecule. Can't really do that. But there are certain techniques that you can use, such as ion traps, in order to hold them in place. For example, you can ionize a gas, and now that it has an electric charge, we can now use magnetic fields in order to confine it into a region in space and hold it still. But even if we do that, we still cannot image the gas because it's said that even though it's held in place, it's still vibrating very, very, very fast. And because it's moving so fast that even if we take a tunneling electron microscope and shoot an electron beam into it, because it's moving so fast that the time of interaction will be so short and brief that it will not be enough to register any kind of change in current enough to create a topographical map of the image. So you
You
can't use
can't
that.
use like a mass spec to
Mass
identify.
spectrometry will only show you the spectrographic, like spectral lines or the readings off of it. That still doesn't directly tell you the shape. Now, when you cool the gases, if you take something stable like helium that is very low temp stable, helium, I think you can get down to like 5 degrees Kelvin and it still remains a gas. I think at like 3.5 degrees Kelvin, it turns into a superfluid. So let's say that you use some crazy tech and you cool it down to 5 degrees Kelvin. It's like barely above absolute zero, right? If you do that and you ionize it, then you can see it'll turn into what they call a Coulomb crystal, which is where the gas molecules will actually begin to take some type of crystalline structure. Now, it's still in a gaseous cloud, right? It's not like a solid crystal, right? It's a gas. But the way they know it's crystalline is if they take that gaseous cloud that's super cold and electrically charged, and they shine lasers into that little gas cloud, it will actually fluoresce or light up in a certain geometric pattern. And if they alter the strength of the electric field that they're using to ionize the gas cloud, the fluorescent geometric pattern will change. So it's the, basically the light show shape will change based on the electric field strength. Now, if that is the case, right, they also say that logic follows towards ion traps, that the the bond angles and the other numerics that they're able to measure and infer based on things like X-ray diffraction and spectroscopy and things like that. When they do that on an ionized gas, the ionization will actually change those numeric values. So the numeric values of ions that are trapped will even be different from the neutral gas molecules. So you're still not even getting the same thing. So it wouldn't even be viewed as evidence of what the neutral one looks like. So there's literally no way for us to directly image a gas molecule. And when we look at things that can infer shape, such as, shining lights into it or doing X-ray diffraction, if we supercool and ionize the gas and we change the electric field strength that's ionizing it, it'll literally cause the geometric shape of the fluorescence to change, showing that the shape is variable, at least on the macro scale. What even is a gas?
It has no definable shape.
Quick question. Are the techniques for this analysis of the shape and form for solids the same as the ones that they use for liquids? Are the techniques the same for the imaging? Do they use the same tool?
That is a good question. I don't know that much about imaging of liquids, but I think that they use the same stuff. But that's just a guess.
Yeah, I guess I'd be making a logical jump here in sort of insinuating that if they've got one for solid, they got a different one for liquid, then maybe there is a third technology, which I would then assume is occulted, or they've basically hidden that specific technique and promoted these other ones. But this hypothesis.
It would probably have. I mean, how would you image liquid though, like that? You would have to freeze it, right, to get it to stay still too.
It's yeah, so it's if you get the liquid to sit still long enough, you can, do it somewhat better than you can a gas. It's still more difficult than it is with a solid, but it's practically more possible than it is with the gas. Like, I know that when you lower the pressure, the evaporation point goes down. So like when you put certain liquids in vacuum, they'll actually start evaporating.
Mhm.
But they do like stuff with like cryogenic stuff. So I think in
So they
liquids
freeze it, yeah.
they'll like do a like a flash freeze type technique.
Yep.
And because it's like the same stuff that they do for like proteins and stuff. That's more like Taylor's realm of stuff. They like flash freeze stuff. But anyways, if you flash freeze like water, for example, right? You'll get like this super thin layer of ice or whatever. And do you guys know about like transition states, like at 32 degrees, like 31.98 or whatever it is? Like there's a number right there where it's like not quite a solid and it's not quite a liquid. It's like kind of in between or whatever.
Yeah.
Yeah, I've heard about that.
The fourth
Yeah,
phase
yeah,
of water.
yeah. Well, it's like right at the transition point between solid and liquid. So like you can keep it in that near liquid state without crystallizing, and it'll like keep it from it'll keep it from losing the liquid structure that it loses when it goes to solid. Because obviously, once it solidifies, it takes a different structure. So like when you do that to a liquid, if you get it just at that right temperature, it'll keep the same liquid shape without actually transitioning into like a solid bond. So that you could try to image that, that would be like the closest you could probably get, like a semi-frozen liquid. Because obviously a fluid liquid that's moving is going to be moving, and it's going to be hard to get a reading on it, just the same way it would be with a gas.
I was going down this rabbit hole trying to figure out if you put water under pressure, like continuously, will it turn to ice or will it just turn to plasma?
Yeah,
It would
extremely
evaporate.
high. Yeah, extremely high pressures will cause the melting point and boiling point to go higher. Extremely low
Right.
pressures will cause the melting point and boiling point to go lower. Because you imagine pressure is just like holding the molecule together. So we know that phase transition is where the molecules become farther apart. And so with a higher pressure, they're compressed. With the lower pressure, they're expanded. It makes a lot of physical sense. Yeah, the lower pressure evaporates more easily. Higher pressure holds the solid form more easily.
It's trippy, dude.
Yeah,
Isn't
so
the
are you,
fourth form of matter gel-like?
Fourth form is plasma. It's ion. It's like electricity. It's like lightning almost.
You're talking of water?
No. Like they're all elements have different phases, right? Like you've got solid, liquid, gas, and then plasma. But plasmas are just when you take a gas and you hit it with enough charge, like enough current, that it becomes even more diffuse than it is in like a gaseous state. Plasmas start doing all kinds of crazy stuff. Like plasmas can actually like pass through like materials and stuff. Pretty
Melt
interesting.
stuff. Yeah.
Right.
Isn't that why they can't do fusion?
Like y'all ever heard of ball lightning?
Yeah.
Ball lightning can go like straight through the walls of a house. It's just like a ball of plasma.
Yeah, pure energy. It's trippy.
Are you familiar with the discussion occurring around like the constituents of water, and as to whether or not water is H2O?
He was in bedroom mode here today.
Your hot mic in, Taylor.
She did. She got it.
This recovery,
dude,
Tay.
I'm with you there, Rick. Is H2O really H2O?
Well, so this is what they sort of landed on, like Peter and Pete. They sort of sum it up pretty nicely: is that water is just water, and that air is dry water. Then they got us some other experiments into also the whether or not air is a constitution of oxygen and nitrogen, primarily. And they do this cool test. I don't want to go into it too much unless you guys are interested, but I'll just give you the layout. Basically, they got on Amazon a product that they sell which claims to separate the oxygen and the nitrogen in the air and puts one out one tube, the other out the other tube. What they found actually is they're filtering it through a medium, and they're creating it. They're not separating it at all. They're just creating a more dense version of oxygenated air. And then if they want to produce what they call a nitrogenous air, which they test by like taking out a flint, it extinguishes a flame. They have to actually put they took out the medium which causes the oxygenation, and instead they put in this special material that creates a nitrogenous response. So they're basically saying like this whole idea that nitrogen and oxygen is like a mixture inside of the air is just completely erroneous.
It's just water.
It's just dry water, and there's some stuff mixed in it.
Well, dude, it makes me wonder if the Aurora Borealis, not to cut back too much, but it makes me wonder if the Aurora Borealis is like, the with the Coulomb crystal thing, you have like a gaseous cloud that's like heavily ionized and very cold, and then you shine like light into it and it fluoresces and turns into like, this glowy thing. I wonder if something similar to that is like happening with the Aurora. If it's like some kind of like ionized gas that's fluorescing everywhere. Just ionized gas streams. Getting hit with like radiation from like the sun or whatever, or the stars or whatever is whatever the light is. Some kind of light's hitting them and hitting whatever's up there and it's fluorescing.
Yeah, that makes sense.
Yeah, it's man,
Crazy
there's
stuff. I didn't know you couldn't
Yeah,
measure the structure of gas like that. That's really interesting. I never even thought about it, to be honest with you.
Yeah, well, dude, the gas model is actually still like, I mean, I wouldn't say it's necessarily quote unquote contested because there's a consensus on everything now because they have such good information control. But like the model of gases, the theory of gases was still being hashed out at like the end of the 1800s and early
Right.
1900s.
Right. I remember the breakdown from J.J. Thomson's hydrodynamic theory of it.
Yeah, like they don't actually, everything that they claim to know about gases is, well, not everything, I shouldn't say that, but a large amount of the stuff that they claim about gases is actually based on inferences of like what would be presumed to be true in their model, because there's only certain variables that they can directly measure, and the other variables are like mathematically or algebraically deduced by presuming a model on the variables they can measure. For example, like in J.J. Thomson's vortex ring theory model, he showed that the as the temperature goes up, that the velocity would actually go down because it would be like growing bigger as like this giant wheel ring, toroid ring thing. But because it's bigger, it has like a larger distance to cover of like the rotation, so the tangential velocity would have to go down if you're conserving the energy. Whereas in the kinetic theory, you get a bunch of little tiny orbs that are bouncing around. So the higher the temperature goes, the faster the orbs fly.
Right.
So it's like, things like that, like saying, oh, the velocity of gases in your room is like several hundred meters per second. Like that's
An
deduced.
assumption.
Yeah, that's deduced based on, using the ideal gas law and a few measurements of different things and deducing a velocity out of it.
Did you brought me back to my 8th grade science teacher when he was saying like if you fart, it's flying around the room at 70,000 meters per second or whatever the fuck. And I always thought like that's retarded. Like what? Then how come I can't smell it when I'm all the way over here, but if I'm right next, like it doesn't make sense.
It's like 300 meters per second or something. I don't know. I mean, dude, 300 meters per second is like 670 miles an hour. So,
But that speed you just told us, that is if no one's even kind of moving, like even in a room that's still.
yeah, because it's based on temperature, right? Like in a room temperature room, the kinetic theory of gases says that the gas molecules are constantly always flying around, bouncing off of each other.
Hmm.
Right. And this is what they believe is like the cause of pressure at surfaces, because the gases are bouncing off of a surface and then bouncing back into the gases above them and then transferring that kinetic energy up through the chain, which is what builds pressure at like a surface. But that's the kinetic theory of gases. Right.
I don't know. I'm not sure if he's still around, but you should definitely run this by BattleMod. He's super obsessed with kinetic gas law.
Really?
Yeah.
Is he aware that the ideal gas law does not hold?
Yeah.
Oh, I'm sure he is. That's crazy. I never heard him talk about that. Really interesting.
Oh, dude, that's his like favorite thing.
No way.
Yeah.
Let me see if he's available.
But I'm still very like doing homework. I didn't mean to throw you guys off of everything. Like
No, you're straight, bro. We're just chilling. We're always like your like little physics factoids or whatever.
Yeah,
little
dude, it's much appreciated.
little Pizio drops we call them.
Piece of Pizio?
P drops. Is that a new P drop? Yo, did we just find out that they can't measure the molecular structure of gas? Sure did.
So you're saying it's just assumptions?
So this little ballistic ball that's bouncing around is just an idealized calculation based on how they wish to interpret it, where temperature is the causal mechanism for the kinetic energy output.
Yeah, dude, everything's waves. That's why even solid matter, there's like de Broglie waves, like there's like a wavelength of matter. How does an object have a wavelength?
Oh, dude, break down the de Broglie wavelength for me, because I haven't looked into it and I was immediately off put by it. By another
by
a separate de Broglie thing. And I was like, well, I definitely don't care about his wavelengths now. So what's up with the de Broglies?
Before you go there, I just want to say it's much appreciated. This is like meditative after that TikTok bullshit. So, all right, hit us with the de Broglie or whatever.
The de Broglie.
De Broglie.
Yes.
So Louis de Broglie, right? Like, was one of the first people. Well, I guess he was the first one. That's why they named it after him. To realize that it wasn't just light that had this like Planck constant relationship going on. That actually there's a wavelength associated with all particles, like electrons, protons, just all matter. So you have this formula where it's wavelength lambda equals h over p, where h is Planck's constant and p is the momentum, which is just mass times velocity. So it's h over mv. And so in a solid, right, like just regular matter, the de Broglie wavelength will measure what they would say is like the, I guess, wave-like nature, not the wave nature, but wave-like nature of particles, of, like the individual particles, like, atoms or ions or electrons or like whatever particles are making it up, And so, like, if you got something that's solid, like take a metal, for example, or even like a semiconductor, because it's important in like computer engineering and stuff.
Mm-hmm.
They say that the particles in there, such as the electrons, for example, behave like waves. And they say that's due to quantum mechanics, right? Like a wave probability function, etc. But they say that the wavelength of those electrons, it's related to their momentum. Okay. And that is important to understand how it behaves in like that solid material. So you got your lattice structure, a little crystalline structure, right? For your little piece of metal.
Right.
And electrons will move through a what's it called? It's a periodic potential, I think it's called. Anyways, it's like basically however the atoms are arranged, right? There's like this band of a region that they can move through that's like wave-like in its nature. So like the wavelength determines how the electron interacts in that region, and it's like wave-like motion and behavior through it. So like the when the momentum goes up, the wavelength gets smaller. And when it loses momentum, the wavelength gets bigger. So like as you increase momentum, as it moves faster, then of course you get a smaller wavelength. And when the wavelength is around the same size as like the spacing between the atoms, then that's when you get stuff like diffraction and interference. So like Bell Labs in the 1920s observed this, that you could actually, not only do X-rays diffract, but electron beams diffract too, just like X-rays do. And it's like, wait, how are we diffracting little billiard balls? Right? So, that's what I'm saying. Like even everything's waves. Of course, that's how they introduce quantum mechanics, because of this curious behavior. Like, how do you explain this?
They had to.
Right. Oh well, the electron's everywhere and nowhere. It's one electron, but it's behaving like a wave somehow. Like it. Yeah, it doesn't. It's retarded.
Think about what Tesla said, dude. Everything in frequency, energy. What did he say? Frequency, energy, and wave, right? What's the three things he says? I'm sorry, I'm eating.
Vibrations, not wave.
There you go. Vibration, frequency, and energy. Or light.
He said one of these things.
I don't know, dude. I'm fucking.
He definitely said some stuff at some point in his life. I think we can kind of
Let me look
agree
it
on
up.
that uniformly.
No one corrected me.
Yo,
Yeah.
I just woke up and the first thing I hear before my coffee is a pee drop. This is like the most amazing thing ever. So
What's
I'm
up,
like,
Sam? Good morning, bro.
wire for the day. Good morning.
If you want to understand the world, consider it in terms of energy, frequency, and vibration. Okay, there we go.
But
Quote
it's really
from
oh yeah, Tesla. It's cool though because when the fact that electrons diffract, whatever electrons are, that's still to be determined, I guess. But you can take an electron beam and shoot it through a material and it diffracts. Like that will actually tell you the like the structure of the material, because basically the electrons will flow through wherever they can fit, and so you can just like shoot electrons as if it's like a super thin liquid through the super tiny screen of the matter,
Dude, isn't
right?
that insane?
Yeah,
So cool.
you're basically, yeah. So it's like imagine if you were to take what's it called, a colander in the kitchen, like a little pot with like holes in the
Yeah.
bottom that you can.
Yeah.
Yeah, so imagine if you were to take a colander and you were to take like some food coloring and some water and put some food coloring and some water and then pour it in the colander and then look out the other side. You can see the fact that, hey, I poured, a cylindrical column of water into this thing, and now I have a bunch of tiny little cylindrical streams coming out of the holes. That tells me that if the colander was invisible, I would know what shape it is because I can see the water coming through the other side, right?
Right.
That's
Yep.
similar to the way that they like use electron beams to image materials of solids. Imagine the electron beam is just like water, and then the solid is like the colander, and they can just squeeze it through it and determine the shape of the solid.
Saying light behaves like a liquid? Get out of here.
Well, it does have a hydrodynamic response
Hmm.
depending on
What was
your direction
yeah,
to the east-west bias.
what's the name of this the server? Oh, Ether. Ether cosmology.
Yeah, that's crazy.
Well, one thing,
Go ahead, Lily.
sorry. One thing about the microscopic world is that, there's no way for us to really, I mean, I guess it's better than the macroscopic world, but there's no way to really become that tiny and determine that everything we saw is exactly how it was, and that somehow whatever images we're seeing, didn't somehow get misinterpreted or distorted, or like there's no way to completely 100% confirm what we're seeing is exactly what is really going on in the micro world. I don't know. I mean, I was thinking of, how in the macro world, like it's hard to tell really, really long distances and stuff like that, like the stars. We don't really know how far they really are and what they are or whatever.
Oh, Lily, it's even worse than that. The reason that you physically cannot and will not ever be able to see things at the atomic level is because, like, an atom is on like the sub nanometer scale. Like, it's in like the order of like tens or hundreds of picometers for an atom, right? The wavelength of light that you see with your eye is like 600 to 700 nanometers. So we're talking about like the size of the light wave in terms of its wavelength is 1,000 times bigger than the atom. So there's no way you're going to be able to see it because the light can't get in there. So that's oh,
How do we know that? Just asking.
how do we know what?
The size of an atom and the size of a wavelength.
Well,
You can split
you
light
can.
through a diffraction grating to measure the wavelengths physically. We can so those can be physically done, and those are like physical measurements, and then the size of the particles or whatever, the subatomic structures would be calculative values based off of energy.
Yeah, we have like Brewster's law and Malice's law. So Brewster's law will actually tell you the refractive index of a of a material. So essentially, you can take an object like let's say like a diamond, right? You say, look, you take a diamond, and you can say, okay, at what angle will the light reflected from a diamond be completely polarized? And actually, every different wavelength of light technically has a different refractive index. Okay, so like for a diamond, the index of refraction for red light is like 2.41, but for purple light, violet light, it's 2.458. So the formula is the tangent of the Brewster angle equals the refractive index. So you can just take the you can take the inverse tangent of the refractive index, and it will give you the angle that will completely polarize the light. And then Malice's law will actually allow you to basically calculate like the intensity of the remaining light after it has been polarized through a filter, and based on the angle of the filter as well. So you can use things like this in order to deduce things like wavelength. Also, you can use Planck's constant and electron interactions and interactions with other materials and things like that in order to figure out the wavelength as well. So there's different ways to do it.
What is Planck's constant for a layman? I always hear of it.
Well, what do they say it is different than what I think it is.
What would it? Well,
They claim that Planck's constant is the constant that determines the energy of a single photon. You multiply Planck's constant by the frequency, and you get the energy of a single photon
okay.
based on the frequency of that photon. That's what they say it is. I think it has to do with the lowest vibrational state of matter, like the lowest quantizable chunk that you can measure out of matter. I think that Planck's constant was actually a consequence of the freaking detector that they were using to measure the light, because any measurement that you take has to come from an interaction. And so they found that like they were able to break down all the values. They took a bunch of values and broke them down, and they were always in these discrete chunks that were multiples of Planck's constant. And they presumed that was because of the photons were discrete, like frequency based energy levels off of this constant. But I don't think it had to do with the light, because I think light's continuous. I think that it had to do with the matter. I think that matter is the limiting factor in the measurement. And who knows? Like, who knows, right? It's possible that that value might even be able to be ever so slightly variable, like for different materials. I don't know if that's true, but like, how would you ever know, right? Like, if it was off by 1% this way or that way based on using a different material, would you even know it, or would you just assume that like, oh, imprecision or something like that?
It's a lot to chew on, bro. And I'm eating right now.
Have you heard of Bragg diffraction?
Bragg diffraction. Wait, what's
Similar-
Bragg's law again?
It's similar to what you were talking about earlier with how with Brewster's angle, where they're measuring. Basically, they'll send in X-rays to a material structure, and then like the angles that it gets deflected off at different thicknesses to it, they take like a differential of that and then determine the molecular structure of it, like the subatomic structure of it.
Okay. Yeah. Yeah, that's what they do for solids,
dude.
right? And then they
Yeah,
use that same reasoning for gases.
Yeah, the Bragg interferometer, dude, it's nuts. Interferometry is so cool. You can measure inside of things, lads.
Can you measure
Explain
how
to
much
me how
love I
matter.
have for you, bro?
I might
Explain
have
to me
some.
how matter diffracts.
I might have some Bragg notes here. Give me 1 second.
Not to brag or anything, but
Might be able to pull up some visuals for the boys. But
anyone else lost in the sauce? Don't be afraid. I'm lost too. I'm learning. It's all good.
oh, I have a whole bunch of stuff.
It sounds like you need to do a presentation on it or something.
Dude, yeah, you know what? Let me add it. Actually,
Time.
we did a reading night of Bragg interferometry once, I think. Bragg / matter interferometry. Future prezzies. Oh yeah. All right, well, we'll come back to the Bragg stuff, but yeah, you check it out on Wikipedia or whatever. It's got some cool images from Bragg interferometers and X-ray. You know, the measurements that they make of molecular structures of things with the X-rays. Very cool.
Word.
So apparently, if you compress water, it turns this weird crystalline structure. Does it turn into a crystal?
Water is a crazy thing in its own. Like it's well, water actually might have memory because it actually can alter its geometric structure based on the vessel that it's kept in. There's all kinds of
Well,
cool fringe research
is,
based on that.
isn't there a state of water where it's like kind of gel-like? Is is could it be that that's what you were talking about when it's in between freezing and liquid?
Like slush.
Yeah. You know that diver that died that went down I think towards Mariana's Trench or something, I can't remember. But remember they said that they hit against they saw like this lake, underwater lake, which was surrounded by clams or something. And then they tried to get inside that water. And then they said they just kind of bumped on it and sprang back up. And so they said it was like a kind of like a solidish, jelly like thing that, that they could not penetrate. So I'm kind of wondering if that is, a different structure of water altogether.
I don't
Do you
know.
guys know who I'm talking about?
Never met her.
That guy that went in, he filmed the Titanic or something like that down there, or they were looking for the Titanic, and then he died mysteriously.
Talking about Tupac?
Huh?
Hey Lily, I think that they were saying that that water was like extra saline or something that had more salt in it, and that's why it was sinking at the bottom. I'm not 100% sure, but if I recall, I ended up watching something on it a long ass time ago too.
Yeah, I know. You're right, because I do remember them saying that it was extra saline, but it was beyond I mean, maybe the extra salinity is what made it impenetrable. But remember what they said? They said that they kind of bounced off of it, but they
What
couldn't penetrate it.
what I was thinking, I was saying is that because it had more salt in it, it was more dense, and they were just too buoyant at their like current capacity to sink their vessel.
Oh, yeah, yeah, yeah. Yeah, you're right. Yeah, so maybe relative to the steel or whatever that vessel, the submarine was made of, this water had like this gel-like bouncy consistency that wouldn't allow them to sink. Yeah.
Talking about a brine lake on the bottom of the ocean.
Yeah.
I've heard it explained as being a brine lake. I don't know if that's actually what it is or not, but it sounds weird.
The goo.
Say like super saline, like a collection of water for some reason there, causing it to be like extra dense.
Yeah.
I don't know if
Yeah.
that's
You
it
know,
or not, but-
Rixie actually made that analogy to. Actually, I don't know if it was Rixie or if it was Roots. Made that analogy to, like, you know how helium rises up, and then let's just say it goes to a spot where it just super cools into like a fluid, and basically that would be the container. Like kind of like how there's like a brine lake, like a goo lagoon at the bottom, right, where it's dense, you can't get through it.
Mhm.
Kind of same thing, but like with
I've
helium
said
as
that
a
before.
superfluid.
Well, I think
Not
Zetetic.
helium, just that the salt, because there's actually a salt layer in the atmosphere. Did y'all know that? A sodium layer?
It's 75
Where?
miles or whatever, I think, right? Or is this what they say? Something like that?
That's what they used to do their guide stars with.
The
The laser
sodium
guide
layer.
stars.
Yeah. Oh, you
Yeah,
know about the laser
it-
stars?
Hey, I need
Uh-huh.
you guys. I need your guys' help really quick. This will only take a second.
9/11.
I need.
I'm sold.
What's
I
up?
need. Hold on. 1 second. Let me make sure that.
You need diamond
sure.
rank in the LOL. Yeah, we get it.
Yeah.
I need you guys to help me out. So, are you seeing me switching between these two YouTube windows right now?
Yes, sir.
Okay.
Wait.
I need help identifying the song that's about to play on here. I don't know
Okay.
who it is.
This